Okay, today we're going to move on and talk about simple machines. Now, when we talk about machines, I suspect the view that most of us have in our minds is something like a automobile or a lawnmower or a printing press, some big complex metallic object that does things faster than we can do them or better than we can do them. In physics, machines has a much different understanding. A machine is any device that magnifies muscle power, that is, that magnifies a force. And right off the bat, many of the things we think of as machines are not really machines in the physics sense. A lawnmower does not magnify muscle power. A lawnmower is something that cuts grass. If it were a machine that we swung a blade at a certain amount of force and it magnified that force so that we could cut down something that we would normally not be able to cut down, then that would be a machine in the physics sense. But the fact that it's more efficient or better at cutting grass does not necessarily make it a machine from a physics perspective. To a layman, the concept of a machine is not the same, since they have to be able to multiply or magnify force. Now, the other thing to remember about machines is, since work is constant, energy can't be created or destroyed. So, as the force is magnified, the distance over which that force is applied has to be diminished. And we will see how this works out as we look at some of the various machines in this lecture. So let's take a look at some different types of machines. This diagram looks at a couple of different machines. These are two examples actually of a lever. And again, as I said, a simple machine is anything that multiplies force. And when you're talking about multiplying force, you have to think in terms of the input of force that you put in and the output, that the force that comes out of the machine. And since the work in and the work out has to be the same, then the force times the distance input has to equal the force times the distance output. The mechanical advantage of any machine is the amount to which the machine multiplies the force. So in essence, the mechanical advantages are going to be equal to F sub 0 in the equation above divided by F sub 1. The ideal mechanical advantage is the mechanical advantage that exists under ideal conditions, that is, excluding the ideas of friction and various other reasons that your advantage is lost. So the ideal mechanical advantage is going to equal to the distance from the fulcrum to the input divided by the distance from the fulcrum to the output, or it's also equal to the force, output force, divided by the input force. The actual mechanical advantage is the true increase in force by the machine, and actually the output force divided by the input force in true situations would be the actual mechanical advantage. The two distances are measured and objective and therefore show the ideal mechanical advantage. The actual output divided by the actual input shows the actual mechanical advantage. And we'll show you this in several example problems. The efficiency is the ratio of the work output divided by the work input. Now, obviously, in ideal situations, this would always be 1, because it's cannot be work or force cannot be work or energy cannot be created or destroyed, but we know that it's sometimes lost in the form of friction or various other reasons. And so these losses decrease the efficiency from 100%. So the simplest of simple machines is called the lever. It has an input arm where the effort is made and an output arm where the load is lifted or otherwise affected, and a fulcrum between the two. The fulcrum is the pivot point of the lever, and the input arm is where the force or effort is applied. The output arm is where the force or effort comes out of the machine and lifts the load. So the distance from the fulcrum to the effort should equal the distance from the fulcrum. The distance from the fulcrum to the effort times the effort should equal the distance from the load to the fulcrum times the load. Now there are three classes of levers shown in this diagram. A first class lever has the effort and the load on opposite sides of the pivot point or fulcrum. The second class lever has both the load and the effort on the same side of the pivot point, but the effort is farther from the pivot point than the load. And in the third class lever, the two are reversed. That is, they're still on the same side of the pivot point, but now the load is farther from the pivot point than the effort is. So first class, the input and output arms are on opposite sides of the fulcrum. Second class, both arms are on the same side, but the output is closer to the fulcrum. And third class is the same as second class, except the input is closer to the fulcrum. If the input arm is longer than the output arm, then the force is multiplied. So in a second class or first class, the force will be multiplied. However, if the output arm is longer than the input arm, then the speed or distance is multiplied. And this is what occurs in a third class lever. So let's take a look at all these concepts in the form of a couple of example problems. A student uses a force of 12 newtons to move a 20 newton massive block. The block is 4 meters from the fulcrum on one side, and the student is 9 meters from the fulcrum on the other side. What is the IMA, AMA, and efficiency? Okay, so how do we go about doing this? So I always recommend drawing a picture so you have a lever with a fulcrum, and the block is on this side, and we'll say that it's 4 meters from the fulcrum, and the effort is on this side, and it's 9 meters from the fulcrum. The effort is said to be 12 newtons mass, and the block is 20 newtons. So this is asking what the IMA is. The IMA is equal to the input distance, which is this distance right here, divided by the output distance. So there's going to be 9 divided by 4, or 2.25. The AMA is the actual mechanical advantage is the load, or the work output, or force output, however you want to say it, divided by the work input, or the force input. Actually, it's more accurate to say force. And this is going to be 20 divided by 12, which is going to be 1.67. And then efficiency is equal to the AMA divided by the IMA times 100. So it's going to be 1.67 divided by 2.25 times 100. And so that is going to equal 74.2%. 74.2% efficiency. The second problem says the center of gravity, that's what CG stands for, of a wheelbarrow and its load is 12 inches from the axle. A woman lifts the load by applying 24 pounds on the handle, a distance 3 feet from the axle. What is the combined weight of the load in the wheelbarrow? Okay, so let's draw our picture on this one. The wheel is like right here, and this is the fulcrum. And you have the wheelbarrow, and the load and the center of gravity for the wheelbarrow is right here, and the woman is lifting right there. So the distance, output distance, is this distance here, and the distance input is right here. And this is given as 12 inches here and 3 feet or 36 inches here. And she lifts 24 pounds. So we know that Fi times Di is equal to F0 times D0. And what we want to know here is this output, force output, which is what this is right here. This is the force input. This is what she puts in. And so it's going to equal Fi Di over D0 is going to equal F0. And you'll notice that the ideal mechanical advantage times the input is equal to the force output. So that's going to be 24 times the input distance is 36 inches divided by 12 inches. So this is going to be 3 times, this is going to be F0, which is 3 times 24 or 72 pounds. Now, that was the simplest kind of machine. That's called a lever. And this is actually another type of lever, just set up in a different way. This is called a wheel and axle. Now, a wheel and axle is a device that's essentially a circular level, with the wheel, which is this part right over here, is being the input arm, and the axle being the output arm. And so the ideal mechanical advantage is going to be the radius of the input, which is the wheel radius, divided by the radius of the axle, which is the output radius. A third type of machine is called a pulley. A pulley combines various setups to increase the ability to lift. A pulley is a device with a wheel and a rope. Now, in a situation like this, what you have is this downward force is multiplied because you have downward here and it also is here. And so it will act to increase the ability to lift, whereas this side doesn't happen. A fixed pulley, a pulley that does not move with a load, that would be this sort of situation. And this is a not fixed pulley, a movable pulley that moves. So here you have a fixed and a movable pulley. The combination of both fixed and mobile pulleys is called a block and tackle.